All right, so before we do the recap from last time, not too much, but still worth clarifying the context. Number one, if you look at the lecture site, you will see that today's notes template, you can definitely find it. Click on the document here, and then you will see the blank pages. If you want to load it to your computer, to a tablet computer, to take notes, feel free. I got about 25 pages or something, but I don't think we can go over all of them, but possibly we have to leave some of them to Wednesday as well. But, doesn't hurt to load them up first. And then, so there is, I slightly changed the title for the slides. It used to be just lecture 1, asymptotic analysis, but now just call it 1A. Because one of the exercises I want to do today is going to involve the predicate logic, which you guys learned from the previous math courses. Things like conjunction, disjunction, universal quantification, etc. I do have a background slides for you guys to look at. So that's something more like a prerequisite in general, but I think I'll just give you some background to really know. As far as this course is concerned, as long as you are brushed up with the math review lectures about the slides, self-study, you should be okay. But we're gonna need those constructs very soon for later, like a looping variance or maybe some inductive proof. We definitely need that, right? So if you click on the 1B over here, that's the slides, right? Not too many, it's just about 13. About excluding the index and title, only about 10 or 11 slides to go over. So pay very much attention to the syntax and also meaning for all the operator as also examples. I also dive into proving or disproving strategies for each of the universal and existential quantification. They will be also useful as well for later, right? I'm gonna remind you maybe again, right? So that's something is really good to get prepared. But we do have some little exercise for you to actually do today. We'll do it together just to clarify the syntax and also a little exercise for you to think about as well, right? As you do the self-study. All right, guys, so this math review is not going to be covered in the class, but if you go over the slides, got any questions, reach out to me, right? It's something you should know, but I want to make sure everybody is clear. Also, pay attention to the syntax about how to write quantification expression. That's some syntax I will expect you guys to follow. If you got any confusion about it, let me know. Okay. Let me see if I missed anything. Okay. And your tutorial 1 from last Thursday, everything is there about the eclipse and also the video. So take a look, and then I think it's a very nice way to warm up about Java programming and also to see the 2D array for this course. We'll definitely revisit 2D array later in the course. Okay, and for this Thursday, I'll let you know. I haven't decided yet, but maybe on Wednesday I can give you a better idea. But very likely we're going to do some paper exercise, some derivation, since we're going to talk about asymptotic analysis today. Okay, and pay attention to the math study. All right. Any questions? Anything that's not clear to you? All good? Okay. I just want to recap very quickly, just one page. Oh, sorry about that. For some reason, okay, so let me just go directly to that page. Sorry about that. Okay. Okay, so this, that's a tutorial. You can definitely follow the recording. So this page is something I want to recap very quickly. Today, we're going to start by going over some basic terms you actually learned from 2101. So, repetition is not bad, just to make sure everybody can recall the important facts about asymptotic analysis. But this one here is really like an important transition. Remember we said from slide number 3 to 17, that will be your self-study. That one there didn't touch anything formal. Just talk about why we actually need something mathematical to approximate the running time. That's also very important context to also study. All right, I'll leave you guys to there. Okay, and then this one just clarify about different terminology, algorithm, data structure, computational problem. Right, these are important things to keep in mind. And this one here just talk about we definitely don't have to worry about this little t, which might be different from platform to platform. So maybe from each physical platform, either mobile device or maybe large computer like a server, you don't have to worry about the t. T simply can be ignored. It can be dropped at some point when we do the analysis. So please revisit this table here about the two different angles that we try to compare, right? Either the same algorithm, but in two different platforms. Or maybe you're talking about two different algorithms, but at the same platform. In either of the two cases, you can simply drop that t t simply is not going to dominate anything for your analysis. Okay? So for today, starting from today, we're just going to focus on more about relative running time. That's what we'll do. Okay? And let me just go directly to the first one. All right. Yeah, this page here, let's just start by clarifying very quickly about basic terms very quickly. And then we'll move on to definition, okay, about big O. And for this course, we only focus on big O. I think for all the running times about the new algorithm, we only do big O. Okay? But for other things, you can easily adapt to the accordingly for the formal definition. Okay? Let's say we got this particular relative running time, right? So given input size n, the right-hand side would be approximately the amount of the primitive operation that will be involved. That's the relative running time, despite the physical platform you're going to execute the algorithm. Okay? So let's write it down again, and I'll clarify quickly some terms. Okay? So let me write it verbatim. So 7n plus 2n times log n. And for this course, if I didn't put the base for the log, you can assume it's going to be 2. Right? If it has to be a different base, like a 10 or maybe 3, any arbitrary number, I will let you know explicitly. Otherwise, assume when there's no base, simply 2. Okay? Like a binary for computers. Okay, log n plus 3n squared. And I'm pretty sure what you learned from 2101 is you simply look for the highest power for the running time. And then that'll be the big O. You should really answer, right? But we'll dive a little bit more into it. It's more to say about just deciding what should be the asymptotic upper bound. Okay, but let's start from that. So this n squared over here is so-called the highest power. Okay, so the highest power for any running time may not be unique, but it should be the highest one, right? You may have n squared appearing maybe 2 places, in which case it should be collapsed into 1 anyway. But okay, so that will be the highest power. So this will be the highest power. So that means asymptotically, this highest term dominates the rest. Dominates other terms. We don't really have to say second largest, like a second highest, or lowest term. We don't normally do that. The highest and also lower terms. Okay? So you can think about the rest. So think about this one here, this term, and this term here. We just say they're lower terms. So this one here, this one here. So these are simply the lower terms. And for each term, you will see something called multiplicative constant, right? You can see for here, this will be 7. You can think about this particularly, for example. It's as if we wrote 7 times n to the power of 0. So 7 is multiplicative constant, right? So here as well, you can think about the 2 over here is also the multiplicative constant. So 7 here, and also 2 here, and also 3 here, right? So they are multiplicative constant. 1, 2, actually, 1, 2, 3. Multiplicative constant. Eventually, when we approximate, lower term have to be dropped anyway. But it's good to know the different terms. Sometimes we may have to refer to them to understand more insights into the algorithm. We'll see. Okay? And then, for example, if you look at this one specifically, okay, this one's interesting. N log n, right? It's a very common running time. For example, merge sort, or maybe the best case for quick sort. Right? We'll see something later as well when we do heap sort. Okay. And this one here, you can think about, let's say, between these two terms. So here you can think about, I simply got n to the power of 1. It's kind of implicit, right? You can think about 1 here versus, let me just try to say, I got this term over here. I'll say blue. I got this term over here, and also log n over here. Right? We can also compare to see relatively which term is higher. When you're asking which term is higher, you're basically asking which function is going to grow faster asymptotically towards infinity, right? So in this case, would you agree? Log n is going to grow more slowly than n. Right? Let's plot the diagram. I think this one may be special enough. We can just brush up very quickly. Right? So here, let me just write down the conclusion first. When you compare these two terms, the blue and the pink, we will say that the log n grows more slowly than the linear n to the power of 1. Right? If you plug these two functions here, I can put another one, like a n to the power of 0. Oh, beg your pardon, I just made a typo before. Sorry about that. So this one here should be just n to the power of 1, right? Implicitly, not n to the power of 0. Okay, I just noticed that. Okay, let's plug very quickly. So let's say we have right here, right? So this will be the f of n. This will be more like a running time, relative running time. And then the x-axis here will be the input size, n. Right? Let's talk about a very special function. This will be the ideal or dream running time for your algorithm, which would be constant. Okay? This would be, for example, here, n to the power of 0, which is just 1. Okay, I put 1 here, right? That means it doesn't matter how large the input size is, the running time is always that constant. Doesn't matter, right? For example, hello world is a constant time algorithm. You always print out that particular string. But we'll see other constant time, like a utility function. We'll see that later. Okay, so that will be 1 to start with, and then let me just highlight it quickly. Okay, let's say this will be the ideal you would like to run into. Okay, what about linear? So linear would be something like this. For example, right? So this will be n to the power of 1, which is n, right? You can see the intersection here would just be 1, right? And also, I'm going to plug in another value here that's kind of special value. Say 4. And then over here, this will be 4. So we can definitely say, asymptotically, this function here grows faster than this function here because it has higher power 1 larger than power 0. Right? Just an example. Of course, there's a spectrum of the running time functions we're going to see. We'll see a chart in the next page. Okay, one more. How about log n? For log n, because we know log 1 will be equal to 0. It's a special case, right? Because 2 to the power of 0 is actually 1. Right? Let me just remind you also quickly. Right? So we know that log base 2, 1. Should be equal to 0 because 2 to the power of 0 equals 1. So you guys may actually want to go back to your maybe 1310, the calculus course, just to remind yourself about what log really means. I think that'll be useful as well. We definitely will see some log when we talk about trees and also when we talk about shortest path algorithm later. Okay? So let's see where log should be. Basically, log is going to sit somewhere in between these two somehow. Right? It's going to grow more slowly than n, but it's going to grow more faster than constant. Right? That's something we'll see. Okay, so that one there we can simply do like that. Right? It's going to be like that. And then this one here you can double check. Log 4 should be 2. Right? Okay. So this will be log n. So this also justifies why the 2 over here is the highest power instead of n log n. Because if you think about n log n is basically somewhere in between 1 and also 0. So that should be 0 point something, right? So this one here, approximately about n to the power 0 point something, just something, visually. So that means this whole thing over here is n to the power of 1 point something. So it should be strictly less than 2. So we don't really choose n log n to be the highest power. Right? So the whole running time over here is going to be dominated by n squared. So ultimately, we're going to say we approximate this running time function as n squared. Okay? So approximation will be n squared. I haven't touched big O just yet because we do need to define the big O formally. But now just a little bit more intuition, visual drawing, and also clarify the terms. Okay? Questions? Oh, okay. All right, sounds good. If you guys do really feel a little bit bored today, I do apologize because the basic stuff. I want to make sure everybody's okay. But don't worry, I got some challenging stuff for you very soon. Okay, but let's get the basic done first. All right, next one. This diagram here, you'll see that on the slide as well. So this one here, just take a look. So this will be the very common running time function you will see, starting from the constant. For example, I'll just maybe highlight a few. Right? You guys can definitely look at that more closely. Right? So for example, you can see constant here basically is going to be stay the same. Basically stay the same. Okay? And then the most expensive algorithm you can have is something here grows exponentially fast. It will be exponential. Okay, let me change to purple, right, just to be consistent. Right? So this will be the most the fastest growing. Okay, over here, exponential, and etc. And the log n that we saw earlier was right here. This is the log n right here. Okay, you can see it's somewhere between the linear and also something else, right? So you can actually take a look. Okay. All right, this diagram here, I'll let you guys follow. Okay, just want to point it out to you. Okay. Any questions? Yeah, go ahead.
Is the log n logarithm, is that what the for?
Yes.
So that would be on the bottom then?
It should be, let me see. Oh, yeah, sorry. You're definitely right. I was thinking about it when I was pointing to it. It should be triangle. Thank you so much. Absolutely. Logarithmic should be right here. And you can see the triangle. So right here. And that one there, you can see is in between this one here is the, logarithmic. Oh, sorry. That's even down. Exactly. I got to follow this. Thank you. Let's be 100% correct. That one there should be right here. Just slightly faster than constant. Okay? And then you can see that this blue here is in between the constant and also linear, which is right here. Right. Okay. You guys can pay attention to more details. Right. Okay. And let's now talk about big O definition. Just before that, let's talk about relevant functions in order for you to define big O. Okay, so let me open a blank page and talk about it, and then we get to it. And I'll give you two possible definitions for the big O. We'll try the standard definition, and then we'll visualize it and some example. And then I want to give you another alternative version using predicate logic. That one there is also a nice exercise to brush up, about how to use the quantification. Okay, we'll do both. So whenever you want to define big O or prove it, you need several functions. Okay. You need two functions, basically. So let's start with the first one. You have some running time function. Okay, so running time, or RT. Running time function. So this one tells you that when you are given some input size, n, presumably larger than or equal to 0, it's going to return back to you some number. Okay. And it's going to be the relative running time, right? So the example will be, if you say f of n equals 7n minus 2, right? So what it is saying is, when you say my input size is only 1, so that means I got roughly about 5 primitive operations involved in executing this algorithm somehow, right? But you don't really have to worry about exactly what those 5 primitive operations will execute like in any particular platform. You don't worry about absolute running time. And of course, if you do maybe 10, it's going to be about 68 and etc. And the running time over here is going to grow linearly as the input size grows. Right? That's why it's called a linear running time function. Right? Right, so we got the running time function there, and we somehow want to see under what asymptotic upper bound family does it really belong to. Right? So we need a second function. And the second function here is called G, just standard, just G. Right? And what we call that is a reference function. You want to use it as a reference. Usually for G of n, one example could be, you might say G of n is simply equal to just n. It's a linear reference function, or it can be log n, can be n log n, etc. Right? What we typically expect to do is we want to manipulate the G of n by some multiplicative constant. Okay? I'll show you visually, but we do expect some further manipulation on G of n expected. Specifically, we need a multiplicative constant. So given G of n, somehow you as a person who want to prove about the asymptotic upper bound, you have to choose a constant c. Okay? This is something that will be expected to be done. But there's some heuristics that you can actually apply about what C should be. We'll see that. Okay? I'm just trying to mention everything together, and then we'll get to the more formal definition. Okay? And given f of n, the running time function, and given the G of n, the reference function, what do we want, really? So the goal is we want to prove something. And the goal is we want to prove that the running time function f of n. So there are different ways for you to see that, to say that. You can simply say f of n is the big O of G of n. That's the most common. We can say f of n is order of big O of G of n. There are different ways. You can look at the slides. I kind of listed all the common saying. You can use any one of them. So we want to prove that this is the big O, asymptotic upper bound. And then we put G of n inside. This is what we want to prove. All right? And let's visualize this very quickly, and then we'll see the formal definition. Okay? So think about this purple is more like a set. And then we say this family here, or a set, is the big O of G of n. It's a family. You can think about the set itself is infinite. It contains simply an infinite number of members inside. Any function that you put inside there will be like a running time function. That running time function must be able to be upper bounded by G of n. That's something we'll see exactly how to formulate it. I'll just write it down. Okay? So if you say that it's going to be all sorts of running time function f of n, okay, we're going to see the different possibility. But any member function here, okay, let's now write it down. So f of n being a member in the family means that it can be upper bounded by G of n. Or to be more precise, this one here, let's make it a little bit more mathematical. So it can be upper bounded by G of n. Of course, the it here is f of n, right? So the star here is the f of n will be less than or equal to. Now here comes a very important point. G of n alone may or may not upper bound f of n. Typically, it wouldn't. However, in order to prove that f of n is in that family, you have to choose a multiplicative constant. So that's the critical step for the proof. Right? That's something we'll do as well later. So this will be something you have to choose, right? So choosing this multiplicative constant here is a very important step for the proof. I'm missing some detail, of course. This is just to give you enough intuition, okay? Questions about intuition here? All good? Okay, let's now talk about formal definition. So this will be the standard one you will see in any textbook here. Okay, let's go over that, and then I'll visualize it. And also, we'll do some little example, and then we'll talk about another alternative definition, okay? So here, you can think about what we are trying to define as f of n. Again, let's remind ourselves, f of n should be some running time function. And we talk about family, right? Right? We are trying to show that f of n is a member of this particular g of n, right? And the g of n here would be the reference function. This will be the reference function. In order to prove that, there are two things we need to specify, two things, okay? There's going to be some multiplicative constant c, which we already mentioned, okay? So c here, okay, c here is going to be a multiplicative constant to change the slope of g of n, right? We'll see exactly, right? And then this part here is something I didn't really quite say in the previous page, right? Now I can say it. You also need another second component. Upper bound effects does not need to start right away when input is actually 0. That will be the smallest size you might have. Upper bound effects theoretically can start at any point because we are really talking about the size of the input towards infinity. Even if the upper bound effect only start maybe around when the input size is 1 million, I'm talking about extreme. That's still fine, right? So you can think about this n0 here. You can see n0, right? We'll get a subscript 0. That means certain starting points where the upper bound effect is going to occur, okay? This will be the starting point. Of the upper bound effects, okay? When I say UB, upper bound, right? Effects. And then the upper bound effect itself is the inequality we just saw earlier. So you can see f of n, the running time, is upper bounded by g of n with the help of some multiplicative constant, right? That's the way to interpret that, okay? And again, this one here, less than or equal to, is the upper bounded by. The definition itself is very, very simple, very concise, but it's just important to visualize what's happening here, okay? So this is also some standard textbook diagram. I simply got it from some textbook, right? This one here is quite nice, except you can see that we only got two functions here, right? We got f of n, the running time, right? So here we got the f of n, the green one, okay? Let's just make sure we draw that. The green one over here. And the reference function, which is g of n, we already multiplied that by the multiplicative constant. We didn't show the g of n alone. We didn't show that. But that's something I will show to you by another example. But let's just simplify that, okay? So now we actually got the... So this will be the reference function. So this will be the reference function, whereas the c here is the multiplicative constant, right? We kind of already showed the final, like the slope changed reference function, okay? And now let's now also highlight it, and then we see something important, okay? So let's look at these two functions, right? Obviously, you can see that if we try to check back the definition, in order for f of n to be in the member of big O of g of n, it must be that f of n should be less than or equal to c times g of n. Is it always the case? Not really, right? So for example, you can see right here. Look at this part here, all right? If you look at this part here, okay, I'll just make it more explicit. Let's look at when the input size is strictly less than n0. You can see there is such a point called n0 right here, okay? So this is when n input size is strictly less than n0. In that case, the running time function here is not really upper bounded by the reference function with the multiplicative constant. So this part here does not really fulfill the equation here. But that's okay. As long as starting from a certain point, the upper bound effects happen, then we'll be okay. Right? So that's why it's very important for you to see the boundary of whether the upper bound effect is going to be satisfied. Right? I'll write it down. Okay? So in this case, you can see that the f of n less than or equal to c times the g of n is actually false. Okay? It's simply not the case that the green one is below the pink one, right? It's not the case. On the other hand, if you try to look at to the right, including the m0 point, that one there is actually good. So starting from n0 and towards infinity, right? If you look at this part over here, right? Oh, we can do better. Okay, so for this part here, we can make the opposite argument. Starting from n equals n0 towards infinity, we have the f of n less than equal to the multiplicative constant that we somehow choose, the reference function, right? So this one here will be true. Right? So that's a critical difference for you to see. So choosing C is definitely important, but you also have to know where that n0 is. The smallest value usually we want to find. Okay? And usually, okay, I'll put a star here. Usually, the smallest possible n0 should be identified. All right, that's good. All right, let's just make one example. Okay, just check very quickly. Okay, let's say this. Let's say we got running time function there, am plus 5. And we got reference function here, n. And somehow you can see the reference function I choose just corresponding to the highest power, right? So the g of n is not really applied to any multiplicative constant just yet, right? I'll do that in a separate step, okay? So now we want to somehow prove the f of n is a member of the family of g of n. So we want to show that here. I can write down. So we want to show that am plus 5 is a member of the big O of n, right? In this example, that's what we want to do. Okay? We'll do the more formal proof a little bit later. Okay? But let's see, for this one here, let's talk about some very particular choice. In order for you to prove this one, of course, you have to choose the C, you have to choose the n0, you have to choose both. Right? But for now, let me say I give you something already. Can you work out the other ones, accordingly? Okay? Let's talk about this one specifically. Let's say I choose the C value to be 9. So which means I'm going to multiply 9 to n. So that means I'm going to consider 9 times n, right? Because n is a reference function by multiplying to 9. Okay? So now what should be the n0 value, right? It's actually very easy to solve. I'll show you that maybe at the end. Okay? But now let me ask, can n0 be a particular value. Okay, so what about n0 here? Okay, star, star. So now the question is, can n0 be 1? When I say n0 is equal to 1, so that means by choosing the C to be 9, is the upper bound effect going to start from n0 equals 1? No? Okay, but you can easily plug in the number, right? Okay, just plug it in. Okay. You're basically asking, so f of 1, which will be 8 plus 5. Okay, and also you can say, also we choose the C to be 9. So 9 times g of 1, which will be 9, right? You're basically asking, is this number over here less than or equal to this number over here? Apparently, no. 13 is not less than or equal to 9, right? False. Okay. So this one just showed to you, if I simply give you a C and N0, I want you to say true or false. Is it going to be a nice pair for C and N0 to show the upper bound effects? Apparently, this one here is not. Okay. Okay, so this is not. So this tells us C equals 9 and 0 equals 1 is not valid to prove it. All right? Okay, follow-up question. If C equals 9, what should N0 be? What will be the smallest value? Yeah? 5? Yeah, that 5 is definitely the answer. Okay, I'll just show you. For those of you who are not sure how to calculate this, right, you can easily do some check. So we're basically saying for certain n0, and then we want it to be exactly equal to, since we choose 9 to be the multiplicative constant, right? And then we got g of n, g of m0, all right? So we start with this. And then we want to see what m0 is. And this one here, we got a times n0 plus 5 equals 9 times n0. Right? You can easily see that n0 should be 5, right? You can solve it. Right? Okay, if you somehow get lost in any of the steps, do let me know later. Okay, so n0 should be 5. Okay, good. Okay, let me do one more visualization. Okay. Okay, having this example set up, so now let's take a quick look, just one more time. Okay, so now this time I put all the three actually functions together, right? So this one here, we don't need to go too detailed, but we start with, first of all, g of n, f of n first. You can see this one here is the running time function right here, okay? And then the g of n is right here. If you only look at the running time function and the reference function, you're not supposed to see always the upper bound effects right away. Okay, so you can see in here, f of n is never upper bounded by the g of n, or you can say f of n less than or equal to g of n, as if we chose a multiplicative constant c to be just 1, right? So this one here, just false. All right, good. So this is why we should choose the c, right? So here we chose the c. C to be 9 and also n0 to be 5, right? That's what we chose. So here you can see by multiplying 9, which is the c value, we actually got 9 times n. So that'll be the manipulated version of the reference function. Once we have that, you can see the pink one right here. That one there is now going to upper bound the reference the running time function starting from a certain point, which is the 5 that we just calculated earlier. All right. All right, so this one here, you can think about right here. Okay, again, this is a critical point for you to see, okay? The upper bound effects starting from m0 equals 5. On the other hand, when n0 is strictly less than 5, there's no upper bound effect just yet, which is okay. As long as there exists this upper bound effect, we are good. Okay? No upper bound effects when the n is strictly, when n0 is strictly less than 5. This is really pretty much the same information, but I'm just trying to put all the three functions into play. All right? Any questions? All right, that's about a definition for big O. Okay. Why don't we take a very short break, and then after the break, we can actually do a little bit example and then talk about another alternative definition for big O. Okay. You can get your iClicker ready. All right, so let's now dive directly into an alternative definition for big O, and then we'll actually try to do examples. Okay. We'll do one mathematical example, just purely mathematical, and then we should really link the asymptotic upper bound to code, like an algorithm, right? That's really the purpose, okay? All right, so let's now take a look at this, okay? And of course, this is something you can maybe try to get some idea, more like a brush up, example for the syntax in predicate logic, propositional logic, but you can think about it, okay? That's the definition we went through before the break, right here. Of course, the critical values would be the multiplicative constant to modify the slope for the reference function. M0 will be the starting point for the upper bound effects. Okay, so these are the two things. And of course, that's the definition for upper bound effect, this particular inequality. So let's now try to formulate the same idea, but now rather than just like a normal standard textbook definition, right? We can make it even more informative, just about using predicate logic, right? Since our input size typically is discrete, the input size n is going to be 1, 2, 3, 4, 5, etc. So we can definitely use discrete math to really to formulate, right? So what we want to do is we want to formulate the definition right here, and then we want to use these operators only. Of course, you can introduce as many layers as you like, and definitely do nested quantification, which I'm pretty sure you saw maybe in the earlier math course. And you can also try to use different operator as you see fit. Okay, I'll start you with. What we really want to do is define this idea about membership, right? It's more like a Boolean in some way, true or false. F of n is a member of the big O of G of n. Right? That's what we want to show. And it will be the case if and only if. Right? You will see if and only if also in the review slides. Right? That's something I will expect you guys to also study very soon after today. Now the question is, what should we put right here? Right? Very likely you will need either the for all will exist or both. Because somehow we want to say the upper bound effects is somehow going to happen at some point and onwards towards infinity. Right? So you're really trying to say something universal about input sizes. Right? How about this? I'll pause for 1 minute. You guys can maybe feel free to sketch. I know maybe it's been a while since you touched the predicate logic, but try to see if anything you can come up with. I'm going to go over the solution with you, right? And then I'll give you one study question for you. That's something you can also try to answer as you try to study the review slides. Okay? I'll just pause for 1 minute. See what you can do on the right-hand side. And the pattern there is actually going to appear actually almost over many times. Of course, don't be too hesitant if you think that maybe I should use a combination, maybe of the quantification, maybe. And the hints, you should really try to look back to this definition here. In some way, we're just trying to formulate all the English text in this definition box into the operators. That's what we are doing. Okay? Okay, one moment, and I'll see if anybody wants to share their thoughts. It's okay to be wrong. Otherwise, I can just give you the solution. Okay. I want to share, right? Okay, you want to share? Okay, one moment. I'll just make sure everybody. All right. Okay, in the interest of time, let's pause right now. Okay. Idea.
If there is some C.
So we want to be more, we want to be practical logic. There's no if, there's any, right? There's no such operator. You want to start with something that's valid for practical logic. Which operator do you want to start with? There exists, okay? There exists what? Okay, that's good. I like it. I'll start with that. That's pretty much matching what I'm thinking here on my notes. Okay, so somehow you can see we want to choose the C and N0. So that means we don't have to choose multiple pairs of the C and N0, just one. As long as there's one valid pair you can choose, then it will fit the definition. So there exists C and also N0. Okay, and then as you will see in the review slides, usually declare dummy variables, right? That will be within the scope of the quantifier. In this case, there exists, right? You got to put a bullet point right here. Okay, that's the syntax. And then, of course, if you like, let's say implicitly, we can say C is an integer. Okay. So the convention is whenever we say the Z here is the set of all integers. So you can think about it as an infinite set starting from minus infinity all the way to maybe -1, 0, and then 1, and then all the way to plus infinity, right? That's an integer. Okay. And then here we got another N0. Okay, N0 over here. You can say it's an integer or maybe natural number, right? I'll also make a distinction here. You can either say integer or you can say natural number, just the set n. But I know in different math course, you may have different definition for natural number. But for this course, the natural number is going to start with the value 0. All right? I know in some course it may not include 0, but for us, we're going to include 0. So it's going to be 0, and then 1, and then 2, all the way to plus infinity, right? So these are the two typical values you may have to use in practical logic. And you will see some example in the review slides. Okay? So I can say maybe the M0 here is really the input size, right? So it cannot be negative. So naturally, we can choose a natural number. It's a type. So I can say here, N0 is a member of the natural number, right? Just implicitly. Okay? And it's very important. C is larger than 0. And also N0 should be larger than or equal to 1, right? That's part of the definition. Let's put it down. So C larger than 0, N0 larger than or equal to 1, right? That's basically what your fellow student just said, right? Continue. Such that, okay, in the case of existential quantification, you basically put a list of strings in conjunction, right? Such that, what? Not if. There's no if in practical logic. Tian Tian, go ahead. Aha. Sounds very promising. Exactly, right? So that's good. I think you're definitely on the right track, but I think I just gotta get used to using the right quantification, right? All right. So what Tian Tian just said over there is actually gonna be this part, such that. All right, so this part, exactly. All right, so this part here, let's now see how we can formulate it, but it's going to be nested quantification. Given a particular C and N0, we want to make sure accordingly we have the upper bound effects starting from N0. Okay, it's going to be right here, right? Going to be giant for all, which is nested within the exist. For every n, the input size, n larger than or equal to n0, right? You can see that correspond to right here. And for universal quantification, when you say such that, it's going to be implication instead, okay? So this will be a little study question I have. I'll formulate it in just one moment, right? So given that n is larger than or equal to n0, the upper bound effect should be there. Okay, let's put the upper bound effects down. So that one there is going to be the f of n less than or equal to c times g of n. All right. Of course, we assume f of n, g of n are already declared outside this scope, so we should be good, right? What I want you guys to think about is right here. Just quick annotation. And here is the input size. Right here. And then this implication here is something I want you to think about, right? Or to figure out. I'll write it on a different page. Okay, let me just see what I have. Okay, it's not here, but that's okay. Study question. For the math review slides. So I'm just going to get the whole thing. That is the correct version. And then let me just copy that. There we go. And then, okay, right here, right? That's our answer from before. I'm just going to change this part over here. What if we change it to conjunction? Is it still valid or still faithful to the actual definition for big O? I can tell you the answer should be no. Otherwise, logic should not be that flexible. And also, implication and conjunction, they're different operators. They don't mean the same thing. In order to answer this question here, you have to review about the definition for these two operators, conjunction versus implication, and then put your own words about having conjunction here in this case versus having implication. Why will one work, but the other one wouldn't work? Okay, so that's a study question for you. All right. Shouldn't be too bad, but if you do want to share your thoughts to double check, you can feel free to speak to me at some point. Okay, I'll leave the choice to you. Okay. Okay. Question? Good. Okay. So I think we got about 20 minutes. I think I'll do a little bit of change just from my end of the flow. I want to do quickly maybe examples, just examples only. There are certain like a big O properties, like an insight I want to also talk about, but let's do that maybe insight sharing, maybe either on maybe Wednesday lecture most likely, or maybe a little bit later, right? We can delay that slightly, but I just want to do examples with you, okay? Let's try that. All right, so this one here, okay, is really about a strategy that you can use to choose C and N0. Okay. So that corresponds to slide number 20, right? Slide number 20 also shows you a very nice little proof about why this strategy will always work. Okay. So let me just talk about the strategy here. But you can just, as long as you can know about this little theorem over here, you can just use it. You don't have to prove it. But I do encourage you to look at the proof itself. It's not difficult, right? Very simple manipulations of the numbers. Okay. So this one here. Okay. So whenever you want to prove that f of n, running time, is a big O family of the g of n, the reference function. Okay? So now, assumption. If the f of n here is polynomial only, polynomial simply means n to the power of something. What would be a violation to this? For example, if your running time involves, for example, log n, that one there is not strictly polynomial. So this strategy here, for most of the time, it will still apply. It can still work, but you got to be careful. But we'll do one example to show to you exactly what I mean by being careful. Okay. So here, if you got f of n, that one there is basically polynomial, exponents only, polynomials only. And for that one there, you will see, first of all, we see the multiplicative constant. Let's see polynomial first. You can see that we, to the power of 0, to the power of 1, to the power of d, we're simply arranging it from the smallest to the largest, right, to begin with. But that's okay. So even if it's not really arranged that way, as long as you can identify the multiplicative constant correctly, you should be okay. So A0 here, A1 here, all the way to A, D. So these are the corresponding multiplicative constant. And notice that multiplicative constant may not be positive always. You might have 7n minus 4. In that case, minus 4 is a negative, right? So be careful. All right, so let's say you're given this. If that's really polynomial only. Number one, the f of n is simply big of n to the d, so this will be the highest power. Okay, that's a conclusion. This will be the highest power. Number one. All right, and then how do we prove it? This theorem gives you conveniently, they tell you guaranteed if that's only polynomial. Number one, the c here is going to be the sum of the absolute values for all the multiplicative constant. We'll see example very soon. Okay, the sum. And notice that the absolute value is very important. All right, and then once you have chosen the c, guaranteed, n0 equals 1. However, that's something I want to put it down here, but we'll see exactly how to deal with it. 1 here, if f of n contains something other than polynomial, for example, log n, something other than polynomial, for example, log n, right? May not be 1, but might be quite close. But I got to be careful to be 100% correct. Okay, just make this note here, and then we'll see example to see. Okay, let's do 2 examples. Okay, so there'll be a very nice closure about the definition and some quick example about proving. Okay, so let's see this one here. Okay. All right, this one here. All right, this one here you can see it's all polynomial. Power 4, power 3, power 2, power 1, power 0, right? It's all polynomial, no log, right? And we just want to somehow prove it. First of all, part 1, you want to decide what's the asymptotic upper bound. Just choose the highest power, right? You can see the highest power is just going to be right here, n to the power 4, right? So it's going to be big of n to the power 4, right? That's nice, okay? But now how do we prove it? Okay, to prove it, according to the little theorem that we just saw, to prove, you have to choose the c and also n0. C will be the sum of the absolute value, which is going to be 5 minus 3. Oh, let me just use a different color. It's going to be 5 minus 3 plus 2 minus 4 plus 1, right? So it's going to be 5 plus minus 3 plus 2 plus minus 4 plus 1. And it's 15. Okay? And since there's no log, there's not something that's not polynomial. So guarantee. And 0 will just be 1. However, I do suggest If the question is really that straightforward, you just want to verify very quickly to see if the upper bound effect really starts from n0 being equal to 1. It may not, right? But the theorem should not be wrong. So you can verify. So what we're going to do is the upper bound effects starts at n0 equals 1. All right? And of course, if you are still trying to get used to the definition, maybe before you reach to anything concrete, think to yourself, what does it really mean when the upper bound effect actually starts from n0 equals 1? That means f of 1, right, should be less than or equal to the multiplicative constant we have chosen to the g of n, right? But in this case, we know pretty well, f is right here. Okay? So that means we're going to have 5 minus 3 plus 2 minus 4 plus 1. And then less than or equal to, and the multiplicative constant we have chosen is 15, right? And 15 times the g of n is right here, right? Just don't forget. That one there, just make sure you actually know how to identify it, right? So this one here, n to the power 4 is the g of n. So that will be the g of 1. So g of 1 will just be 1 to the 4, right? Right, if you do the math, 15 less than or equal to 15. So that one's good. So nothing to be done further, right? Strictly speaking, the verification in this case will not be necessary because there's only polynomial in the running time, right? It's guaranteed by the theorem, but it doesn't hurt, just to give you more confidence. All right, so this one's done. All right, questions about this one here? All right, simple proof. I would suggest we do one more, okay? Give me one moment. As I said, I'm going to skip the discussion about like a various property about big O. We can do that maybe on Wednesday or maybe a little bit later. Okay, that one's not as urgent. Okay, okay. So we can skip these 1, 2, and 3 pages just about property. We'll revisit these very soon. Okay, just keep them maybe handy in your tablet or on your computer. Okay. So there are various examples I have over here. I would suggest I'll only do one of them with you. That one's the trickiest one. We could do it. And for the rest, it will be up to your practice. I'll give you a solution maybe a little bit later. Okay. I would suggest we do number 3 right here. All right. If you look at this one here, it's not really meeting the condition for applying that little theorem. Because you can see that it's not just a polynomial, right? Because if you look at that, this one here is really 2 times n to the 0. That one is polynomial. But this one here, not really. However, I would suggest we still apply that. But you got to make sure you verify to make sure n0 may start with 1 or maybe something a little bit bigger. Okay, so that will be my tip for you. Okay, so let's so there are 2 parts over here. So what would be the most accurate asymptotic upper bound? We choose the highest power, right? And we already talked about between constant and also log. Which one grows faster? Log, right? Good. Okay, thank you. So part 1, it should be big O of log 1. Big O of log n. Big O of log n. And then the n here, the log n here is the g of n. That's part 1. Okay, very easy. I want to just highlight, highlight exactly what g of n is. We're going to use it. Okay. Okay, part 2, prove your claim. Okay. So to prove it, you basically have to choose a C and N0. Let's follow that theorem again, okay? With the precautionary mind that this may not be exactly n0 equals 1 because we have log, right? No guarantee in this case, okay? So number 2, we choose C equal to, right? Multiplicative constant. We got 3 here, and also we got 2 here, right? These two. So 3 plus 2. And that would be just 5. Oh, actually, I should be more careful, okay? That's my bad. Put absolute value so you get used to it, right? Otherwise, sometimes you forget, you only put negative value. In that case, you can make mistake, right? Gotta be absolute value. And now we say n0 maybe should be 1. However, we have some reservation. So verify. How do we verify? Right? Again, the way we verify is like before. You somehow want to check to see whether or not, so this equation here is important, right? This inequality. When f of 1 is it less than or equal to c times g of 1? The same thing. We want to double check again, right? Let's go back. So we want to verify. So we want to try to see if f of 1 is less than or equal to c times the g of 1. Right? Question mark. All right? And then the function here is the 3 log n plus 2. Right? So 3 times log 1 plus 2. For those of you who might be calculating ahead of me, you might see this sum problem already, right? I will get there. Less than or equal to, and the c we have chosen here is 5 times, and then g of 1. The g here is log n, log 1, right? Okay. So now, log 1, would you agree, is 0, right? That's something we saw earlier. So 3 times 0, 3 times 0 plus 2, 2, less than or equal to 5 times 0, false. Which means if you simply put n0 equals 1, it's incorrect, right? So now in this case, what should you do? I would say in this case, you simply keep this c over there. It's a very nice choice, but it may be that the upper bound effect is just going to happen a little bit later. So try maybe a larger value for maybe n0. Okay, I'll let you do as exercise. Okay. So the next step is try a larger n0. Maybe it's simply equal to 2, right? If that one works, great. So that means you got a valid pair for c equals 5 and n0 equals 2. That's great. If n0 equals 2 still doesn't work, try another one. You wouldn't take too long for you to get there, right? Questions? Okay, okay. 8 minutes. I would suggest, let's see here. I think the rest, okay, number 4, number 5, right? You guys can give it a try. You also see the answer on the slides, but I'll give you a little bit more, like a steps when I post the solution, right? You can just see the very concise solution on the slides already, okay? So up to here, these are the examples just about mathematical, right? Given f of n, g of n, we want to prove something among them. That's something we have. But more relevant to this course and also to 2101 is you somehow want to apply this theory here into algorithm, right? So let's now consider example, okay? So I do have, let's say 1 here, 2 here, and for this example here, I will do 1, okay? I will actually do number 3 together with you. Number 3, okay? So for number 1 and 2, 1.1, 1.2, and also 2. And also here, so that will be up to your exercise, right? Again, I'll give you a solution later, but we'll do one of them, okay? Before that, we got to cover some very quick basics. I think we can cover just the basics today, and then we'll continue with the solution to the exercise on Wednesday, okay? I think that's about right. So let me just, there are 2 things I want to talk about, okay? Let's start with something here. In some way, sometimes when you are trying to figure out the running time, most likely you have to analyze the behavior of a loop, and very likely nested loop. In that way, it's very important for you to also count about how many iterations you have. And in order for you to calculate the number of iterations, you want to see the bounds for the loop counter, right? So in that way, you have to be very careful about counting, okay? So let's see some very practical notation that will be very useful when we go back to the example on Wednesday. So let's say we want to calculate the size of integer interval. Okay, specifically, whenever we are writing square brackets a comma b, a and b are simply some arbitrary integers, arbitrary, okay? And we assume that, a and b, they are integers. And also a less than or equal to b. Let's assume. There might be some special cases, but we'll worry about that a little bit later, okay? That's the assumption. And given this interval, we're asking the following question. How many numbers are in this interval? How many? Right? And just before we see the little formula, very easy to see, but I would rather you guys not try to memorize it, because you might, if you forget about, like a certain term over there, you're gonna get a wrong answer. Okay? Just to start with, this is something you may have seen in your calculus class when you actually got this as opposed to a parenthesis, right? The square bracket here is called closed interval, meaning that the endpoints a and b should be included, right? So at least two numbers, basically, right? So this is a closed end. So that means the end value should be included. All right? It turns out the size of the interval will be b minus a plus 1. But I want to spend just 1 minute. I have some very quick visual justification, very quick, okay? B minus a plus 1, okay? But how come? If you try to visualize what's happening here, let's say that's a number line, right? Maybe starting from 0, doesn't really matter, just number line. Let's say this number here is b. All right? B itself tells me that there are b numbers. B can be 10, that means we got 10 numbers, right? That's what I meant, all right? And then we actually got a somewhere right here, right? So now we want to ask about how many numbers there are, how many points, starting from a inclusive all the way to b inclusive. The way to do it is think about b itself tells us about how many points we have to the left of b, including b. And then we want to include a. So we should really find the left point to a. That would be a minus 1. And then you simply use b, subtracted a minus 1 from that. You should really get how many numbers you got exactly right here. Okay, I'll write it down. Okay, quick justification. And this one here is going to be a minus 1. Okay, you can think about, given b right here, if I simply take out everything up to and including a minus 1, I simply take it out. What's left over here is going to be all the numbers starting from a all the way to b, inclusive. So another way to think about this formula is we are really doing b minus a minus 1, which will be exactly the ultimate form you will see. Okay? So doesn't matter which one you would like, but whichever, pick your pick. Right? Normally, I just remember that as b minus a plus 1, but just justifying that quickly. Okay? How can this be useful? Let's just do one example, right? For example, let's say, how many numbers are there between 34 to 100? How many? You don't need a calculator for that, I hope. 67. Okay, awesome. All right, good. Another way you can think about, another useful application. Think about array. Let's say I got an array. Array index always start with 0. Agree? The A is always fixed to be 0. And then there's got to be some maximum valid index for the array. Let's say the X over here is really about the max valid index. The max valid index. And the 0 here is always, okay, I'll finish this in 1 minute, okay, and then I'll let you go. This will be the minimum index, okay? And this one here, if we apply the formula, the length of the array is going to be x minus 0 plus 1, which is x plus 1, right? So the size of the length of the array is always a maximum index plus 1. That you can also use that formula to understand it, okay? So this formula here is actually very important. We're going to use that for the example we need, all right? Okay, so that will be it, and then I'll see you guys on Wednesday.